Okay, good morning, guys. For those of you who don't know me, my name is Gary Robertson. I'm a real-time engineer with Linaro, and we're here to talk today about some of the considerations involved in choosing between the Linux with the full real-time patch or operating in a core isolation environment. And this talk is intended to be targeted at applications developers who might be considering the use of one of these low latency, high performance type environments for their applications. It's really not intended to be a status report for the kernel development behind these things. And I have to say that I am not an expert in that kernel development. Really, my only involvement with that has been in merging some of the patches into an RT-patched kernel and into our main LNG kernel tree. So I'm only marginally aware of the details of the code involved. I think I do have a reasonable handle on the issues. Excuse me. I originally used the term issues, but some people had issues with that. So in consideration of that, I will say considerations is a more accurate term. So I do think that I am aware of some of the considerations which need to be made here. And I'll preface this, being an old gray-headed dinosaur. When I first started computing, and in the early days of computing, you literally booted your application on the computer, and your application was the only thing running on the computer. So there were no issues of scheduling latencies or anything like that. Instead, you had to worry about how many iterations of a busy loop you had to run before you could push out the next character to your peripheral. The computers were pretty big and expensive in those days, and so it didn't take long till somebody decided that, you could get a lot better use of those resources if you would, when you had a program that was waiting on a peripheral, you'd swap it out and run somebody else's program, and thus a scheduler was born. And then in about 1976, you began to get more or less wide adoption of microprocessor-based computers, and the computer made it out of the gigantic commercial and government installations and became more or less ubiquitous. Started getting into everything. We started using 16-bit computers and 8-bit computers in embedded and industrial applications that hadn't been possible before, and of course that has mushroomed into the places we are today. As we started to use computers for industrial type applications, latencies became important. And so the first thing that people did was they developed specialized real-time operating systems. And then in around 1991, 92, when Linux came on board, everybody started, a lot of people started using that. But of course it was not, it was a time slice type environment, and it was not well suited for real-time applications. And so they, Ingo Molnar and some other folks started working on that and came up eventually with a real-time patch. The goal of this patch was to basically shrink the range of possible latencies so that they were deterministic and predictable, and at the same time to as far as possible to retain the same programming environment that you had in a non-real-time system. To do that, they used some macro magic, which took a lot of the spin locks that were used in areas where you couldn't sleep, like interrupt handlers, things like that, and they magically transformed those to be based on a new locking primitive called an RT mutex. And the RT mutex uses priority-based queuing and priority-based waiting, and it puts the application to sleep. Now, obviously you can't put an interrupt handler to sleep, so One of the things that they did was they encapsulated the actual interrupt handlers inside of schedulable threads and then left a little stub in the actual interrupt vector so that when the interrupt vector was hit, it would stimulate the schedulable thread, which had the actual interrupt handler inside of it. That was pretty amazing. It had you know, it had its good points and its bad points. The good points are that on the applications level, at least, most of these things are transparent. You can still use all the existing stacks and interfaces and everything inside of the kernel. And it works on single CPU platforms, which, when this was started, were still the most predominant things, especially for embedded applications. The bad points that there are a lot of places where you suddenly have a sleeping lock in a context that does not have the requisite data structures to wake back up. And so if you take an interrupt handler that's a real interrupt handler running from an interrupt context, and he tries to hit a spin lock, which has magically been transformed into an RT mutex, and it puts the interrupt handler to sleep, you know, things go bad. So it's required a lot of changes to different places in the kernel, and also in a lot of interrupt service routines that were written into drivers and that sort of thing. The other thing about it is that the threaded interrupt handlers typically operate at a real-time scheduling priority of about 50, which is in the mid-range. They did that on purpose so that if you really have a critical applications thread or something, you can actually preempt the interrupt handlers, and the onus is on you as a developer not to preempt them for too long. But the downside of that is that it's really easy to hose up your system rather badly if you set your real-time priorities you know, improperly. So it demands expert tuning to get the right performance out of the system. Okay, the real-time patch, because of this high maintenance overhead, has been really slow in making it into the mainstream kernel. The threaded interrupt handlers made it. The RT mutexes themselves made it. The priority inheritance for other kinds of mutexes for applications has made it. So a lot of these things are there, but there's still quite a bit of maintenance overhead associated with it. And Thomas Gleixner and I think Greg Cole-Hartman have been working on maintaining this stuff. But it does take a lot of time and a lot of money. And apparently there have been a lot of people, a lot of users out there, but until just recently, nobody was really anteing up any financial support for it. So a few months back, they indicated that unless something changed, they were going to discontinue their maintenance and support for the the official maintenance of the kernel, the RT kernel patch. I just heard a couple of days ago that apparently there has been an infusion of money, so at least the patch will be maintained for a while longer. I think previously it was scheduled to, the official maintenance was supposed to be discontinued after 3.16. Hopefully now that will be extended somewhat. But because of the overhead involved, it's still an uncertain future. We really don't know whether it's likely that this will ever fully make it into the kernel.
What are the pieces that are missing for most users?
I'm not really sure what all the issues are. I think they are fairly substantial. The things that are needed to, and I apologize, but I read that some while back, and right now I'm too jet lagged to remember it. but
I thought it was like 80% merged. All the important bits are already there, so very few people need something more than what we already have.
I more or less agree with that, but I think the things that haven't been merged are the more troublesome bits and the things that would be more time-consuming to integrate smoothly into the rest of the kernel, and that's what I think puts it in jeopardy. Okay, so these days, if you have an application that is substantial enough that you are going to require an operating system, more than likely you're going to have a multi-core CPU that it's based on. That's not entirely true, but increasingly the multi-core SoCs are ubiquitous. And so we now have come not quite full circle, but full spiral, so that you now have the CPU core resources have become inexpensive enough that you can once again afford to literally run only a single application thread in a particular core. And so there's been some work in the kernel, and we're fortunate that a couple of the guys, at least, who have done a good bit of that work are here to keep me honest today. So there's been a good bit of work in the core, in the kernel to allow core isolation and something called full tickless operation. And the general idea there is to remove all the kernel overhead from your from contending with your user space application. And so this depends on having multiple cores, because you're still going to have at least one core that's dedicated to doing all the kernel housekeeping issues and that sort of thing. And let me back up a little bit here. There are a couple of components to it. The first of which is something called the scheduling domains and C groups, and then those things have been kind of combined into something called CPU sets. And what that allows you to do, the scheduling domains, and their memory, I forget the term they use, is it zones or, but at any rate, the scheduling domains are there to allow the schedulers to be confined to a particular range or particular subset of the available CPU cores in the system. The CPU sets take into account the memory zones and the scheduler domains and allow you to conveniently group and manipulate those resources, so that just using those things you can confine or affine both interrupt handlers and schedulable tasks to a particular set or subset of the CPU cores. By default, it starts off with one large set that contains all the available cores, and so anything can run anywhere. And you can then set up a hierarchical system to create subsets, so that you can then migrate some of these things and separate out your different types of applications and housekeeping tasks and that sort of thing into specific cores. On top of that, then, there's now something that a couple of guys here in the room had worked on that's called full tickless operation or full no hertz. And the idea there is that one of the things that used to stimulate scheduler activity was the timer tick interrupt. And if you get to a point where, first they decided that if you're in the idle task, there was really no point in running a regular time-based interrupt. And then that was extended and said, well, if you're going to have only a single schedulable thread running on a core, there's also no reason to impose that burden. If there's no reason for anything to be scheduled, there's no reason really to run the scheduler tick per se. The trouble with that, though, is there were a lot of other housekeeping things that were kind of tied in with the scheduler tick. And so there's been quite a bit of hard work done to allow us to kind of divorce ourselves from having to have that scheduler tick on an isolated core. So you have CPU core isolation in conjunction with full tickless operation, and that would, I think some people have called that zero overhead Linux. That would be as close as possible to the days of yore when the operating system essentially was a program loader and a set of callable utility libraries, so that your program can be isolated on that core. It can use the operating system to load itself and initialize all the data structures and that sort of thing. And then from there on out, the operating system gets out of the way. Now, once again, you don't get something for nothing. So your pluses on this are that you eliminate most of the contention from the operating system and from other threads or tasks for running your application in an isolated core. So you really get maximum performance out of that application. You also, because you're not swapping out tasks, you're not getting memory mapping overhead or anything like that. You have to disable core migration. Basically, there's load balancing algorithms in the kernel in general that says essentially, for various reasons, I think the energy aware scheduler may move things around for in order to reduce the power consumption. But generally speaking, if you have one core that's doing very little and another one that's swamped, the schedulers will attempt to migrate processes from the heavily loaded core to the other one. And there are a lot of heuristics involved there where they decide whether or not it's worth the trouble to move the thing from one core to another. But basically, by using the core isolation, you avoid all these things. And again, you have just moved all the kernel overhead that's possible out of the way of your user space application. The downside of it is that essentially your user space application has to run, again, like we did in the old days, with more or less direct I/O access. If you try to use any conventional interrupt handlers or drivers and they are running on that core, then you lose your full tickless operation. And because of that, it also demands that someone who knows what they're doing, sets this stuff up to operate properly and keep things in the full tickless mode. And once again, also, if you still have an application that is running on a monocore unit processing platform, this isn't going to work. Oops.
I guess most ARM platforms also wouldn't work if you have to do DMA into user space because it's not cache coherent on typical SoC.
Okay, that's one I was not aware of. But yeah, there are a lot of issues associated with once you get this stuff isolated, essentially you're very limited in the system resources that you can take advantage of without breaking you out of the full tickless mode.
No, it's just is that a problem on the whole architecture or just on some hardware?
On ARM CPUs, you cannot have a user space driver with for hardware that does DMA unless you have cache coherent DMA, which very few have. At the
So
moment.
as if we've got hardware that's designed for these use cases.
Yes, that would work.
Would work. Okay.
Yes, but
That's the expectation.
yes, but 90% of the ARM hardware is not designed for this use case.
Right. Okay.
Yeah, and that's a consideration I wasn't aware of. Yes.
So, question on the previous slide. So maybe
Can-
maybe you can give more kind of like specific example when if I have actually user thread running on isolated actually CPU, and let's say actually I do actually system call and it like go through the socket and then actually through the NIC. What you're saying after that, this core is not isolated anymore. So it's just start. Basically, when I come back, my expectation actually kind of when, if I come back from this actual system call and don't do those actually anymore, I'm still running actually isolated. Are you saying that during this actual system call process, something actually will happen that kernel will start using this core again up to some extent, or?
Let me say, for one thing, that it's possible to use the system calls and everything to initialize your application prior to going full tickless. Okay, but once you go full tickless, anything that causes your application in that full tickless core to sleep is going to break you out of full tickless mode. And pretty much any system call nowadays is potentially preemptible. Hopefully, because typically each core is running its own scheduler, and in your isolated core, you're not the scheduler isn't really active, and there isn't anything else contending on that core. So you might be able to get away with it, but it's not safe. You know, I mean, anything that happens while you're in the kernel that puts the kernel part of once you're in that system call, puts the system call to sleep, is going to break you out.
I understand actually kind of during actually the call, yeah, sure, this kind of isolation is broken, but once actually I come back from is it actually kind of this core after that becomes poisoned and kind of like kernel start doing any activities on this actual core after that, or?
That's a detail of the code I'm not sure about, and maybe Kevin or Varesh can.
If you still just have your single thread, once you get back to user space, you'll still be tickless.
It resumes full tickless? Okay.
Any reason to enter the kernel whatsoever, it basically just you turn off tickless. But once you come back to user space, you're still tickless.
That's what I thought actually. So it's basically it's not a good idea for this sort of application to do those things. But if they done, it's not breaking anything. Once you come back, you still kind of running.
However, I mean, you still have to be able to check because you're entering the kernel might have kicked off an interrupt handler that's going to kick off an IRQ thread, which now you'll have two threads running on that core. If it's if IRQ pinned that CPU, you enter the kernel, you had IRQ. Now you got two threads, so you're not tickless. So you might actually come back to your thread, and you're still sharing with an IRQ thread for a little bit. So you might not be tickless right away, but if things settle back down, you can still be tickless. And I don't know that there's not standard mechanisms right now to say I'm running, but I'm actually in tickless mode. So yeah, once you enter the kernel, you're kind of all bets are off for a while anyway. And you still got to make sure that things quiesce down.
You have to know what you're doing if you want to call the kernel.
Yeah, because there's a lot of kernel things that are still pinned to CPUs. You can have IRQs pinned to CPUs. You can have work queues pinned to CPUs. You can have broadcast IPIs, and so there's still stuff like that that can get in the way. So you don't always know.
Wouldn't the reserving of a core for tickless operations unpin those and make sure the core
It doesn't
It wants
unpin
to,
them.
But there are things. I mean, the kernel has you can request and drivers can request to have things that are pinned to CPUs, and so you can't just refuse to pin those things. And you can have pin timers, you can have pinned work queues and stuff. So there's various subsystems. Anybody can request
And
it.
you don't necessarily want those to be unpinned. They're going to be asleep while your single-threaded application is running. They may still be pinned on that core, but they're dormant, and they need to be there when the current. If for some reason you're broken out of full tickless mode, then you need those things there. So you don't necessarily want to remove them from that core.
But down to this needing a lot of tuning bit. You can find out what those subsystems are, and if you don't need them, turn them off and find out why some of those things are pinned and disable them if you don't need them. But yeah, some of the things you actually want there.
Yeah, one of the examples is CPU flag, which gives a per CPU timer, a pin timer. So you really cannot use CPU flag right now on the isolated cores at all, unless you're using the performance governor or the power saver.
There were a couple of other things which I'm not, there were concerns that I don't know enough about the code to be sure of. One of those was task migration. That there were some tasks which are critical and need a CPU to run on, and it was my understanding that if one of those tasks could not find a CPU in the subset CPU set, that it would jump up a level and might bridge over to a separate CPU set that shared the higher parent level. And I don't know under those circumstances if it would be possible for some critical system task to find itself needing to run and there were no cores available at the time, and it might pop over into a full Ticklish core. That won't happen?
At the CPU set level, you can completely disable load balancing, and you won't have tasks going between CPU sets that are isolated.
What
Okay.
if all other CPUs are hot plugged, like they're unplugged?
Oh, that's right. Yeah. So hot plug throws a wrench into this. Yeah. Yeah. I think this actually hot plug breaks this right now, and I don't think there's a. It's actually the hot plug is fine because it'll move everything. It'll just kill your CPU sets and move them over. It's the replug, I think, that doesn't know how to bring things back. Yeah, hot plug is a whole nother wrench.
Yeah.
A big one.
Yeah, basically, if you want to do this kind of stuff, you also shouldn't. There's a number of things that you basically can't do, like CPU frick, CPU idle, hot plug, all of those.
CPU idle's fine.
CPU is fine.
Well, depending on what your real-time requirements are. If the CPU goes to idle, you will have a latency of coming back, and you might want to latency.
Yeah, that's true.
And that's a nice segue to the last item here, which is the interaction with thermal management. Because if you've got your core running full blast, by definition, if you've got one thread running there, that thread is running 100% CPU utilization. And if you've got the clocks turned up all the way and you're running full blast 100% on that core, it's questionable whether you're going to overheat the core or not. And it's also, apparently, it's SoC specific as to the degree of support for not damaging the hardware.
Well, there you'd have a thermal driver that would actually have to kick in and cap the frequency.
And that would run on another core, theoretically?
That's another
That
thing
could
you
happen
shouldn't.
on the housekeeping core.
So that's what I would assume had to happen. But somebody was telling me that because I thought maybe this was going to be a component of the energy aware scheduler, since in my mind energy consumption and the heat levels are intimately related.
Well, if you're serious about real time, then you also wouldn't be able to use the thermal management.
Right.
Basically, the only thermal management you have to do is if you exceed the TDP and your fans don't keep up, you shut the system off.
That's not necessarily good.
Well, then get bigger fans.
But yeah.
But I mean, that comes into system engineering. So
Yeah.
that's
Yeah.
getting into the category of you have to choose a machine
that has the support, but these are considerations that need to be dealt with.
and they're good. So, but I don't think we need to get stuck on these issues, because that's system engineering issues. If it's going to derail from what you're right to talk about.
That was one of the things that what I wasn't certain about, just how well that had been considered, since all this core isolation stuff is pretty new, and as Kevin mentioned, it's not all well integrated with everything else yet.
Conversation at a time, please. Sorry, go ahead.
That was all. Okay, so I think there may be a middle ground here. If you use only the CPU sets and core affinity and don't try to worry about the full tickless, then a lot of these considerations go away, and you still go a long way toward being able to isolate your latency-specific or performance-specific applications from contention with other system threads and user threads and resources. And so since the threaded ISRs and the priority inheriting mutexes, et cetera, have made it into the mainline kernel from the RT patch, I think that it's quite possible you could just use the CPU sets and CPU affinity without worrying about full tickless and wind up with kind of a sweet spot where you're not really restricted with the types of system calls you can employ, but you have achieved sufficient isolation to minimize your latency jitter and that sort of thing. So this is something that I think we need to do some measurements on. I was hoping to have some measurements to show you guys. We're working on some performance measuring software. Unfortunately, didn't get it ready quite in time for this presentation. And so that's the end of my presentation.
Even if you don't have any real final numbers, do you have any idea of the latency distribution here with this solution?
Well, if you run a high priority RT task in a normal environment and it's CPU bound, there's something that's called scheduling throttle, or I forget the exact term, but basically they have a percentage of the available CPU bandwidth which can be allocated, and the reserve right now I think about the upper 5% of the CPU utilization, so that you don't get the CPU intensive high priority task doesn't completely shut out everything else. So
you can disable that. You can disable this RT throttling.
okay,
It's up to you. You can set.
but if you're not running in an isolated core, you certainly don't want to do that. So I can testify from doing real-time development back in the days when that wasn't there.
In Linaro, are we doing testing right now on the performance that we're getting? Like,
Not yet.
Do we have numbers or statistics?
Not yet.
Are we working on it?
I am, yes.
Okay.
Yeah, up until this point, what we've done is just check to see how long we could maintain full tickless isolation.
In this example, you wanted to say it will work without no hertz full, this middle part?
Well, it's basically what server admins have been doing for ages. It's just if you want to reduce the jitter, you isolate things as far as you can without doing anything sophisticated, and it helps. And you get.
But are we using ISO CPUs instead? Because in this case, the tick will at least disturb every 5 milliseconds or something.
Yes,
So
and if you don't care about every 5 milliseconds, that's okay. Because most people won't care. Some
But
people will.
Right, so there's going to be two issues. There's going to be latency and there's going to be throughput. And if your primary concern is throughput, and if once in a while you have latency due to jitter, if that's okay with your application, then this may be perfectly fine and it reduces your engineering costs. But if your application is really affected by jitter every once in a while, then this still isn't going to work.
Yeah.
And it's that classic real-time problem.
Yeah, but with no hertz full, I mean, this says normal AP environment. With no hertz full, with full tickless, you essentially have all this stuff anyway.
Yes.
It's just that if you use any normal API or kernel calls, you fall back to this, and if you don't, you end up with both. So it's like
Okay, well, that's a good point. That,
So
that
it's
was,
like,
again,
my question, I guess, is what's the difference between this and the running an isolated core, but you happen to have a couple threads running? You get all this stuff also.
there is none.
Yeah, there is.
And I mean, that's one of the benefits of it, is that you could have a multi-threaded application here. And the question I have is, I would think that if you're in an isolated, if you have moved, if you've migrated everything possible away from that core, and then you're running a more or less conventional application inside that core, that when your scheduler tick does happen, there probably will be minimal work for it to do.
Yes.
So your jitter is probably going to be minimized.
Right, so that's the question of if you can handle the scheduler tick.
There are other alternatives to real-time Linux other than core isolation and preempt-RT. Have you considered them?
I'm sorry?
Hello?
Yeah.
There are another alternatives to having real-time Linux systems other than preempt-RT and core isolation. Have you considered using those?
Using them together.
No, something like Xenomai or RTIA. For your purposes, because you get I mean, basically you get better latencies with those.
Okay. So
The microkernel approach.
Right.
yeah, so
Right.
running an RTOS type kernel inside the isolated thing, is that what you're?
No.
No?
No, RTA is, it was a completely separate kernel, where the Linux kernel would run subservient to the real-time kernel. And the real-time
Yeah.
kernel would assign a few cores to Linux.
That's what I thought I was talking about there. You have basically an RTOS. I guess, yeah, it's a little separate thing, similar to what they used to do with Windows, where you basically have an RTOS, and the non-real-time operating system takes the leftover CPU cycles and runs.
Yeah.
Mm-hmm. Yeah.
Most of those environments have ended up becoming either difficult to port or just not very well maintained.
But-
So,
Okay.
I mean, there's always the push to go back to the Linux kernel because we've already got all the driver support in there, and in theory, it will just work. I mean, that's always been the gold standard, do real time in the kernel. But there are people who are deploying that.
Yeah, I mean, I'm aware of that. I've been working with those systems for
Yeah.
many years. We've got projects like Xenomai
Yeah.
that were supported. I think today we are supporting 3.16. The support for ARM is very good, as it is for PowerPC.
Well, the
So,
idea here is actually to migrate away from using proprietary RPCs.
this is not proprietary. This is open
The
source.
thing about that is, if we lose the organized maintenance of the full RT patch upstream at kernel.org, then inevitably whatever they left us with is going to wind up being maintained in a fragmentary manner, and so you're going to wind up with, a vendor-specific, shop-specific adaptations and enhancements of whatever
Okay. So
they left at.
Here's another aspect which LNG is just kind of touching on now, is we're not always looking at the embedded type development process, where you've got a vendor who takes the software, takes the hardware, and bundles it up into a single package, which is a router or whatever the product is. We're now looking at a world where NFV is becoming worse, so network function virtualization, where you actually have three different software vendors. You have, three different vendors. You've got the hardware vendor, you've got the operating system vendor, and then you've got the application vendor that's doing the network function. And the operating system vendor is someone like Red Hat, who doesn't want to do some kind of custom kernel. They want to be able to do this sort of thing, but they want it to work out of the box with their existing network stack to allow the network function application vendors to build on top of that. So that's one of the things that's been really desired about being able to do everything in Linux, because it's just another Linux application.
And commented on that, and I'm going to repeat myself, but a project like Xenomai, you can install support for Xenomai through apt-get on Ubuntu and on Fedora. It's a minimal installation-wise. It's an effortless task.
As I see them on a gradual scale. So on the far end, you have something like Xenomai, or even further would be a classic RTOS. Then you have Xenomai, Then you have the preempt RT, then you have core isolation on the other end. You have something like what you showed last that's just gone from the screen, where you just use the regular kernel APIs to isolate the cores little more than they're usually isolated, and just run Linux task. And the gradual shift over time has been further in this direction, because it's becoming good enough as processors get faster, and spending 1,000 cycles is less of a cost in the end, and you have more cores, so you don't care if one core does all the management. You cannot just do more by just doing isolation. So we're starting to use more general purpose software for the things that used to need strong real time.
Yeah, but you still want the determinism, right? And it doesn't matter.
Well, a lot of people thought they needed strong determinism, when actually they found out that they're fine with what we already have in Linux, which is not strong determinism, but it's good enough.
Yes. But as an example on this is, I know one project was managing a piece of silicon. It was a A6 control, and all the control was done from user space using Xenomai as a real-time provider. Latencies were about 20 microseconds. That's an example of an easy and simple way. I mean, it was a very short project, and that is on the market today. And this is why. And it's a very. What I keep on saying is that Xenomai is a very well-maintained project that I don't understand why it's not contemplated along with all the other options. No.
Oh, okay. So,
That's all.
let's not. Just to be clear, this work doesn't say that work's not valuable.
Yeah,
Right.
there are good
This
use
is a
cases for all
particular
those
use
things.
case,
Yes.
This is a particular way that, especially in the LNG, that we want to go, but that does not preclude vendors who want to use Xenomai or already have software there,
Oh,
or they prefer the model to do that, to go and to ship products that way. In fact, from those of us in the Linux kernel, we're totally cool with that.
Right. I mean.
That's totally fine.
No, but okay. So sorry.
Yeah.
I've just been reminded that we're running over our time here. It is 12 o'clock, so if anybody has somewhere else they need to go, feel free.
Is there another group in this room?
That's possible as well.
Let me check. I believe there's another session.
Okay, so we need to get out of the way of this next session. Thank you guys for coming. Appreciate it. I hope it was stimulating.